Don't forget to subscribe and ring that bell.
A, how you do it. Me, I'm doing fine because I just got my hands on the 2023 AP Calculus free response questions. And what better place to start than with problem number 1? Yes, we do get a graphing calculator for this problem. Luck be a lady tonight. But we would have been fine without it because we're awesome, and we're awesome at math. If you need a calculator, I say this every time, get a TI plus 84, TI 84 plus CE, the color edition. It's so much prettier. And you don't even have to get that gray and yellow bland school one. Okay, even though the gray is pretty sweet. There is a whole slew of colors that you can pick from. Links in the description below. Yes, my personal calculator is a TI 84 plus. The one I use in school at my desk, the one I use at home, but it is that sexy, sexy mint green. All right, let's get started with free response question number 1. Okay, number 1 reads, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second. This jumps out to me right away because that tells me that this is a rate. Okay? And t is measured in seconds since the pumping began. Selected values for f of t are given in the table above. If you know anything about what I do when I do these videos, I love graphs and tables and charts. Oh my. So this is great that we start with one. 1A says, using correct units. This means I better label it and label it right. I never have to put a label down unless they state that. Using correct units, interpret the meaning of the integral of f of t dt from 60 to 135 in the context of the problem. Don't just say that an integral is area under the curve. Integral is the sum of these numbers. You're going to have to, in the context of the problem, use things like gallons, seconds, probably gas, okay? We want to relate what that integral represents specifically for this problem. And let's start with just that, all right? So let's go. And then there's actually something to do afterward, but let's first tackle this part right here, okay? So using correct units, interpret the meaning of the integral from 60 to 135 of f of t dt. The integral from 60 to 135 of f of t dt is, okay? Now, one of the fundamental things you need to know about calculus is the following. If I have a rate, okay, or a first derivative of something, or this can also be velocity in terms of position, velocity, and acceleration. But for this problem, we have gallons per second, okay? And I integrate that. I'm going backward. That would give me just the units, not the units per time, just the units. So in this case, it's just gallons, or gallons of gas for this particular problem, okay? So when we integrate, we are going to get just the gallons. Okay? That is so important to know. And of course, if I have gallons and I take the derivative, that would give me my rate. But we're going backward. So the integral is the total number of gallons. That takes care of correct units. Okay? The total number of gallons of gas. That takes care of context of the problem. Okay? So the total number of gallons of gas pumped, because that's what this individual is doing, pumping gas, from time equals 60 seconds to time equals 135 seconds. The 60 and 135, those are my bounds. And how do I know it's time in seconds? Well, there's multiple places. Right here in the table, our rate is per second. It tells us in the Problem number 1, time is measured in seconds. Okay, so several places. That's the first part. That was easy. Interpreting that was the easy part, in my opinion. IMO, baby. So what's the second part asking us to do? Let's use green. Green is my favorite color. Using a right Riemann sum. I knew we were going to do that as the moment I saw we had this table here. We were going to have to do some sort of trapezoid rule or Riemann sum with 3 subintervals. Now they tell us from 60 to 90 is one interval. From 90 to 120 is the next interval. And from 120 to 135 is the third interval. And they want us to approximate the value of that integral. Okay? We don't need a label or anything. They just want a number. It's fine. And why did I use those 3 colors to underline the intervals? Because I like to color coordinate my boxes. Now, first things first, we are not using 0 seconds or 150 seconds. Please note, okay, because this is where people make mistakes, I'm only going from 60 to 135. I start at 60 in my first interval. I end at 135 in my last one. So please do not use this column where time is 0 or this column where it's 150. All right, we're just using that inside. So the first interval goes from 60 to 90. So I kind of draw a rectangle here. And that has a width between 60 and 90 of 30. My next rectangle in my Riemann sum goes from 90 to 120. Okay, and this again has a width of 30. That, am I saying triangle? I mean rectangle. I don't even know. I have to go back and watch it. I probably won't, so. And last but not least, from 120 to 135, okay, that has a width of 15. Okay, so there are the 3 rectangles I'm going to add up the areas of. And anytime I do a right Riemann sum, you see my y values. So this going to be an x, this would be a y. I have 2 y values, 0.1 and 0.15. But this is a right Riemann sum. So I want the right value, which is the 0.15. And I multiply it times my width of 30. So I get 30 times 0.15. And I add that to the red rectangle area. Again, I have 2 points. I have, oh no, I hit the red one. 0.15 and 0.1. But again, I'm with the right side. 0.1 is on the right. I multiply that times my width of 30. 30 times 0.1. And last but not least, I do the same thing to my blue rectangle. Again, I got 0.1 on the left, 0.05 on the right. This is a right Riemann sum, so I'm going to take my 0.05 and multiply that times my width, which is 15. Now, you are a smart person. I don't doubt that. But you know what? We get a calculator here, and this is timed. So quit wasting that time and just type that in the calculator, will you? Did I get that right? I did. And if we do this correct, let's go view, attached to LCD. I'll put that below so I can see what I'm actually typing in. And I get, okay, 30, and there's my 0, times 0.15 plus 30, and I'm onto the red portion, times 0.1 plus, now I'm onto the blue, 15 times 0.05. I hit enter, and I get this fantastic number, 8.25, which is actually the answer to the second part of 1A. Okay? So I'm going to go here, and that is 8.25. They don't ask me in terms, I could write gallons, but I don't need to. That is the value, the approximation using a right Riemann sum of the integral of f of t dt from 135 to 60. Okay? We answered that perfectly. Good job. All right, 1b. Must there exist a value of c for which c is in between 60 and 120, such that derivative of c equals 0? Oh. For 1A, I told you that there was a give me, an absolute must in calculus for you to understand, going from rate to unit, right? Integrating back from rate, it gives you the unit. Or taking the derivative of something with units and you get a rate with respect to time. Here, you absolutely have to understand, and I'm feeling a little purplish, the mean value theorem. All right, so what does that say? Remember, this is our x, this is our y. We'll call it, I know it's t and f of t. But so between when x is 60 and when x is 120, right here and right here, between this point, okay, there has to be a derivative at one point where it equals 0. The mean value theorem says if something is differentiable everywhere and continuous everywhere, they tell us it is right here. Okay, that my change in y over my change in x has to equal the derivative at some point. Instead of putting an x here, they make that a c. How come? Because they put x's here, I guess. Okay, there has to be some point in our interval. Now, my interval goes from 60 to 120. So let's do our change in y over change in x of the above figures. Meaning, we'll call this one y2, this one y1, this one could be our x2, and this one could be our x1. So let's go ahead and do that. So 0.1, and then that's at 120, our y2 and x2. And we got 0.1 for y1 and 60 for x1. That's 0 over 60. That is 0. This right here is 0. 0 has to equal the derivative of c somewhere. It has to. That is a theorem. It is a gimme, as long as it is differentiable, and they tell us that. Okay? So yes, there is some point. They're not telling us to find the point. Just explain, must there exist a value c? The answer is yes. All right? So, justify means show math work. Guess what? We just did right here. All right? So let's answer the question. Yes. And I'm going to get a little fancy because by the mean value theorem, okay, f prime of c equals y2 minus y1 over x2 minus x1, okay, which equals 0 in this point, okay? And we have the math work to justify that right over here. Oh, look, we got arrows going in both directions. Look at how fancy we are. It's like we have a flow chart. Oh, we are smart. 1C, the rate of flow of gasoline in gallons per second can also be modeled by G of T. All right, well, what they're saying is this is gallons per second. Okay, the rate of the flow in gallons per second, okay, now we don't need the table. They give us an equation that can represent it. There it is, and it's G of T. Okay, so it can be modeled by G of T, which is T over 500 times the cosine of T over 120 squared from time 0 to 150 inclusive. Now, using that model, find the average rate of flow of the gasoline over that time interval from 0 to 150. Show the setup for your calculations. You don't need to show the exact calculations, but you need to show where your number came from in the setup. All right? Here you go. Anytime. And the main concept here is whenever I'm finding the average of something, it's not the average slope. It's the average rate of flow of gasoline. What is the rate of flow of gasoline? G of T. So if this is G of T, and it's a rate, and I want to find the average value of that rate, I just integrate the rates. Please do not forget to put dt. You will get points taken off if you don't have a dummy variable. And I'm doing that from 0 to 150. But anytime it's an average, I always got to multiply that by 1 over the difference in my bounds. This right here denotes average value. Whenever I multiply 1 over the difference in bounds times the integral. The whole thing gives me the average value, okay? But I integrate things left and right all day in calculus. But what makes it an average, not a total, when I multiply by 1 over the difference in my bounds. Now, the good thing is here, this is the setup. It's done. I'm doing a lot of arrows today. I'm just going to put that in a calculator. And I'm going to substitute my equation in for GT. Man, I wish they were all like this. This is nice. So let's turn this on. And we are going to start with a fraction. And we're going to put 1 over 150 minus 0. Mister, can't I just put 1 over 150? Sure you can there, little Timmy. Sure you can. But I let the calculator do all of the calculations, even though 150 minus 0 is 150. You'll get the same answer. I just like to type it in exactly as I have it written, okay? With the exception of g of t won't be there, the actual equation will be there. Times math 9 from 0 to 150. And I'm going to put, okay, a fraction here. Because we don't use t, we're going to use x over 500 times the cosine. Make sure your calculator is in radian mode, not degree mode, okay? And the cosine is going to have another fraction in there that's squared. So that's why I have another set of parentheses. X over 120, pop that out and square it, because that square should be in those cosine brackets, dx. That's it. This right here is my g of t. And then we got dt for a dummy variable right there. Okay? So I hit enter, and I should get 0.09. I'm going to make that up to a 6 because the number after it is 5 or bigger. All right? So that's going to be approximately 0.096. They don't ask for labels, so, I mean, that's all I'm leaving. Boom. I mean, but it's an average rate of flow, so that the average rate of flow will be 0.096 gallons per second. All right? But they don't ask it. I don't leave it. Simple. The final section of free response question 1, 1D, right in your face. Using the model G defined in part C. So let's just write this off to the side. Well, there's no side to write it. So remember, G of t, that equaled t over 500 times the cosine of t over 120. This was squared. Right? That's what G of t was. Okay, so using this model that we got from part C, find the value of G prime of 140, then interpret the meaning of your answer in the context of the problem. If you weren't watching this for 1A, when they say context of the problem, okay, I'm not just going to say, when I describe the meaning of my answer, I'm not just going to say it's the derivative of G. Okay, I've got to use, in the context of the problem, it's gallons, there's gas per second. Okay, so these are words that I'm going to have in there because it is specific to this problem for the gas station pumping gas here. Okay, you have, in the context of the problem means you have to use the actual words in the problem in the scenario. All right, so first of all, G prime of 140. Okay, so first of all, let's find the value of that. I mean, guys, oh my goodness, guys. All right, if I go to math 8, I'm going to take the derivative of my equation, G of t, right? It is x over 500 times the cosine. I'm going to do another parenthesis because this fraction in here also needs to be squared. So it's x over 120. Pop that and square it, dx. Now look what, yep. When x is 140. At what value of x do I want to take the derivative? When x is 140. Now I want to point something out quick. You see how I have these two things here and I square it? When I hit enter, it puts it outside the fraction. When I use alpha y equals to create a fraction, it will always do the fraction first before it applies anything. So do I need these parentheses here? I do not. But I just like to be careful, especially when it comes to my math. I hit enter, and I get negative, well, 0.00. I'm going to make this a 5 because the number after it is 5 or bigger. So let's go here. That's negative 0.005. All right, that's the answer. Well, let's interpret what that means, okay? It's the derivative of g. So in this case, I have g, and if I go this way and I take the derivative of g, I get g prime. This is the rate of whatever g is. So let's look and see what g is. G is not just gallons, okay? G, if I go back to part C, G is actually already in gallons per second. They gave me a function that was a rate. They didn't put a little apostrophe here for derivative. They didn't have to because they stated that is gallons per second. So if I go back down here, this is already gallons per second. And I took the rate of it. So it is the rate of gallons per second, how it's changing. All right. So we want to write this. We want to write it as follows. It is the rate of flow. And why did I say the rate of flow? If I go back to 1C, this is the problem I'm using, right? This is the, wow, look at what, wow, that's crazy. It's the rate of flow of gasoline. That's what G is. So I'm going to use those exact words. It's the rate of flow of gasoline. And I've already began to write this in the context of the problem because I'm using flow, the rate of gasoline, okay? The rate of flow of gasoline, since this answer is negative, my rate of flow of gasoline is decreasing. Okay, so my rate of flow of gasoline is decreasing at 0.005. Now it's gallons per second, and you could say gallons per second, because that takes my rate to another rate, or say gallons per second squared. Either one of those would have been fine. But when, be specific, at time equals 140 seconds. Be specific. There you go. We are done with free response question 1. It ain't so bad. Only 23 minutes. And you know, I start these videos out talking for a minute. So really, 22 minutes. I'll probably talk for another minute now. Screw you. No, I'm just kidding. Just kidding. Glad you're here. Glad you watch these videos. And you know what? Stay tuned because I will put out free response question number 2 in the very near future. See ya.
Don't forget to subscribe and ring that bell.